Polynomials, complex numbers. Mentioned this before, but if you notice, all the coefficients of our polynomial are real numbers, so no imaginary numbers in there at all. Then the solutions, or the roots, if you do get complex solutions, they will always be in conjugate pairs. Now, the reason for that is every polynomial can be factorized down to be a combination of quadratics and linear functions. And so if it's a quadratic that can't be factorized with real numbers, we know we can do it with complex numbers, but we'll get plus or minus the square root of the imaginary part. So that's where it comes from. So every polynomial can be factorized down to be a mixture of quadratic and linear factors over real numbers, if we just use real numbers. There are some quadratics that are what we call irreducible, so you can't bring it down to linear factors. But if we go into the complex field, then they can all be broken down. So whatever the degree of the polynomial is, that's how many linear factors you would end up with. So quadratic 2, a cubic 3, and so on. But what that does mean then is every odd-ordered polynomial must have a real root, because if the complex ones or the imaginary ones are appearing in pairs, you'll always get an even number of those. Therefore, if you've got an odd polynomial, there must be 1 left over, or 3 left over, or 5 left over, and so on. Start with a simple quadratic. So x squared plus 2x plus 2, before we knew about these complex numbers, we'd say, oh, hang on a sec, multiplies together give 2, adds together 2. Yeah, you can't do that. We'd go to our quadratic formula, we'd get a negative number and go, whoa. But now, and I'm doing it by the completing the square method here, I can go, well, actually, that'll be x plus 1 squared, but to balance it out to get the 2, I must be plus 1. But instead of plus 1, I'm seeing it as minus I squared. So difference of 2 squares, there it is. X plus 1 plus I, x plus 1 minus I. So there's the conjugate pair. Let's go to this quartic. Well, it's actually a quadratic when you look at it, because the powers are going down by an even amount. So we can treat this one like a quadratic. It's just that the pronumeral is z squared rather than z. So what multiplies together to give negative 12? Adds together give 1. Yeah, actually that one works out quite nicely. There we go. Z squared minus 3, z squared plus 4. If I was just dealing with real numbers, I could factorize it down partially to linear factors. The first one is difference 2 squares. Alright, we end up with the third root 3, but that's still a number, that's not a problem. The second one, z squared plus 4, I couldn't do. So that was if we're just dealing with real numbers. If they asked us to factorise over real numbers, we would stop there. If we kept going, then the z squared plus 4 is also difference 2 squares. Instead of seeing 4, I'm looking at it as minus 4i squared. I get plus 2i minus 2i. That would be over the complex numbers, and now we could solve that. There it is, plus or minus root 3, plus or minus 2i. You may recall our factor theorem. If x minus a is a factor of a polynomial, then we know we get 0 when we substitute it in. And that's true with complex numbers as well. If it's x minus some complex number, when we substitute that complex number in, we should get an answer of 0. Now, if the coefficient of x in this linear factor is not 1, so ax, still the same idea, but now we substitute fractions in b over a, so the constant divided by the coefficient of x. In fact, that's what we're doing with the other one as well. It's just that the coefficient of x is 1, so a over 1 is a. But that's the idea. It's the constant number divided by the coefficient of a. That's what we check. If I'm asked to then do this one, then 2x cubed minus 3x squared plus 8x plus 5. It's a cubic, so I know it does have a real one. So I guess the trick is to look for that first. That's going to be the easier one to find. Pick a logical substitution to put in. You try for easy numbers. 0. No, it doesn't work. 1. No, it doesn't work. Next logical one to pick, of course, is negative a half. Well, maybe not. Oh, well, look, it works. That was lucky, hey. So something negative a half, we get the answer of 0. Therefore, I know the factor is 2x plus 1. That allows me to then go and find the other factor, do it via a polynomial division. I could do it by a bit of logic, looking at it and say leading term times leading term, things like that. The second factor is a quadratic. Once it's down to a quadratic, I don't have to play around with the factor theorem because quadratics are easy to factorise. Hopefully this one is. Multiplies together to give 5. Oh no, that one doesn't come out nicely. Alright, I'll complete the square on it. So x minus 2x would give me x minus 1 squared. It would then be plus 4. That's why it wasn't coming out nicely. We're going to get imaginary numbers here because I see plus 4, but I'm thinking minus 4i squared, which means it's x minus 1 minus 2i, x minus 1 plus 2i, so the conjugates. There it is, factorised all up. Ooh, a quartic has 2 rational zeros. Well, rational numbers are real numbers, so they're basically telling me there's 2 real solutions. Find them, and then go and factorise completely over the complex field. We've got to think of a logical thing to substitute in. We know it must go into the constant number. So 3, well 3 is a prime number, so that's good. So I could try 1 or 3. Of course they might be negative numbers, could be negative 1 or negative 3. But because it's monic, it could also be divided by factors of 4. It'd be lovely if that factor was just 1, and so I'm just trying 3 and 1. But if 3 and 1 don't work, maybe I try 3 over 4 or 1 over 4. And if that doesn't work, 3 over 2 or 1 over 2. But it's got to be a factor of the number 4. So all those possibilities. What did I try first? Yeah, of course, a half. Oh, it worked. Wow, got lucky. Substitute in a half. Of course, that's not the first thing I would have tried, by the way. I would have tried 1 and things like that. But a half works, so I now know 2x minus 1 is one of those rational zeros that they're talking about. That's the factor that would produce the answer of a half. Okay, let's find the other one. Now I now know it's 2x minus 1 times something. Sure, I could do a polynomial division. Personally, I prefer to just do it using a bit of logic. Remember, leading term times the leading term must give me the leading term. So 2x times what gives me 4x to the power of 4? Well, it's 2x times 2x cubed. That must be 2x cubed. The constant times the constant must give me the constant. The negative 1 times what gives me negative 3. So I know the constant there is plus 3. Okay. We have some missing terms in the middle. How many x's and how many x squareds? If I was to leave it like this, how many x's would I have? Well, 3 times 2x is 6x. I want x. How do I get from 6x to x? I have to subtract 5x. Therefore, this negative 1 must have been times 5x. Now we have to work out the x squareds. It doesn't really matter. X cubed or x squared. Let's go with x cubed. At this stage I have minus 2x cubed. I want plus 8x cubed. How do I go, what did I say it was, minus 2? From minus 2x cubed to 8x cubed, I've got to add 10x cubed. So I need 10x cubed. So it would have been 2x times 5x squared. That would give me the missing 10x cubed I've got. So that's how I do it by logic, I guess. But remember, you've always got polynomial division you could fall back on if you think, whoa, that might take me too much time. Some of the others are simpler than that, and you could do your polynomial division, you'll get that factor. Remember, we're still trying to factorise this cubic now, but we still got the same rules. Could still be a factor of 3, or 3, negative 3, 1, negative 1. But this time now I'm not going to try over 4 because I know now it's got to be a factor of 2. It's either going to be 2 or 1. Okay, which one did I try? Oh, of course, negative 3 on 2. There you go. Negative 3 on 2, it came out to be 0. I now know the other rational 0. 2x plus 3 is also a factor now. Okay. Found the zeros, those rational zeros. 1 is a half, 1 is minus 3 on 2. That was the first part of the question. Now complete the factorisation. There's my polynomial. I know those two things are factors. There must be another factor. It must be a quadratic, because I've got to end up with x to the power of 4. Let's work out that missing term, because I know the leading terms will always give me the leading term. So I've got my 2x, I've got my other 2x, I have 4x squared, must have been times x squared to get the 4x to the power of 4. I've got that one. Constants must multiply together. Negative 1 times 3, it must have been plus 1 in the other one to get negative 3. The question now is, how many x's? Well, get that middle term. Well, here it is to the side, my working out here. How many x's have I got? Well, I've got 1 times 3 times 2x, 6x, but I've also got 1 times negative 1 times 2x, negative 2x. At this stage I've got 4x. How many do I want? I want 1x, therefore I need negative 3x. That's why it's negative 3x. So I'm now saying negative 1 times 3 times what will give me negative 3x plus x. Again, you could do polynomial division. Now let's factorise x squared plus x plus 1. I'll do it by completing the square. Not nice, it's fractions, but anyway, it's okay. Fractions, if that's what they are, that's what they are. And there is our factorisation of that quartic. If you're not comfortable with that logic idea, use your polynomial division. That will get you the required factors. Alright, let's do another quartic. This time the hint they've given me is that it does have a real root. Its multiplicity is 2. Here's all the things I can check. The real roots must be a divisor of 45. So it could be 1, 3, 5, 9, 15, 45, of course it could be negative any of those as well. Thank goodness it's monic. It's just a 1z to the 4, so I don't have to try all those fraction ones like I did before. It's just got to be one of those. But you'll notice I found the derivative. Why did I do that? Remember the idea about multiple roots. If it is a multiple root, then not only is it a solution to the polynomial, it's a solution to the derivative as well. It's going to be easier to factorise the derivative because it's a cubic, not a quartic. It's easier to substitute in. So when they tell me multiplicity 2, so it's a double root, hence why I can use the derivative. Again, 1's the logical one. It doesn't work though. So it's not 1. Which one did I try next? 3, sub it into the derivative. Yes, potentially this is the double root. Remember, it has to be a solution to both. Substitute it into the polynomial itself. Yes, it works. We've got the double root. It's 3. X minus 3 squared, multiplicity 2. X minus 3 squared is a factor. What is the other factor? So z minus 3 squared. I know I have to end up with z to the power of 4. Therefore, that must be z squared. Constant times the constant gives me the constant. My constant, remember, is not negative 3. It's negative 3 squared. So it's 9. 9 times what is 45? 9 5s are 45. Okay, how many z do we have? If we were to expand out z minus 3 squared, it's probably going to be easier. So what will we have? We'd have we'd have z squared minus 6z. Okay. So minus 6z times 5 is minus 30z. We want minus 30z. How many have we got? Minus 30z. Beautiful. There is no z term in that second factor. That is the other factor. Z squared plus 5. Okay. It says solve it. I didn't actually have to factorise this, you know, because all it said was solve it. I could go straight to the answer now. Z is 3, or z is plus or minus root 5i would be our solutions. Okay, z squared equals negative 5. Let's do the 2022 question. 16D. It was the last question on last year's HSC. So you're thinking, it's a bit more involved. We have to find all the complex numbers that satisfy these three things at the same time. So the modulus of each complex number is the same. They're all got the same magnitude. When we add them up, we get an answer of 1. And when we multiply them, we get an answer of 1 as well. What are these three numbers? That's it. They gave you no more clues or anything. You had to go from there and come up with an answer. What did I do first? Well, this is how I approached it. I said, well, if they multiply together to give 1, then the magnitude of that is 1. Because the magnitude of 1 is 1. So, alright, I know the modulus of whatever complex number when we multiply Z1, Z2, Z3 together is, I know the size of it is 1. Okay. But we said the modulus of these are the same. So mod Z1 times mod Z2 times mod Z3 is the same as mod Z3 cubed. And that's 1. The magnitude of Z3 must be 1. But that also means the magnitude of Z1 is 1 and Z2 is 1. So we know that now. The magnitude of each of these complex numbers we're looking for is 1. Now if I play around again with the multiplication, Z1, Z2 is equal to 1 on Z3. In other words, it's the reciprocal. And the reciprocal is the conjugate on the modulus squared. And we just said that conjugate is 1. So I now know that when I multiply Z1 and Z2 together, I get the conjugate of Z3. But of course, I could have done that with any of them. I could have rewritten it and said Z1 times Z3 is the reciprocal of Z2, and so on. So that's got to be the same for all of them. Z1 times Z3 must be the conjugate of Z2, and Z2 times Z3 must be the conjugate of Z1. Okay. That now tells me that I could write Z1, Z2 plus Z1, Z3 plus Z2 times Z3 as the conjugate of Z3 plus the conjugate of Z2 plus the conjugate of Z1, which by our rules is the same as saying the conjugate of Z1 plus Z2 plus Z3, which they've told me is 1, and the conjugate of 1 is 1. I now know what Z1, Z2 plus Z1, Z3 plus Z2, Z3 is. It's also equal to 1. Now where is this heading? That means Z1, Z2 and Z3 are the solutions to that. Right? Because remember how your polynomial is set up. You start with the leading term. The next one is the solutions one at a time. Alpha plus beta plus gamma. The next one is the roots 2 at a time. And then the last one are the roots 3 at a time. And I know these things. We have found them all. That is the polynomial that will give us the solutions Z1, Z2 and Z3. Now all I got to do is solve this cubic, and I have the three numbers. Let's solve the cubic. X minus 1 is a factor. That's nice. X minus 1 times x squared plus 1. Therefore x is 1, or x is plus or minus I. There's the three numbers. Now it doesn't matter which one I call Z1, which one I call Z2. They're really just saying what are the three numbers, and there they are. Exercise 1G. I photocopied something from Patel for you. Some nice questions there as well.